Section 6.1 deals with using another technique of integration called integration by parts. And they're kind of showing how it's developed by using the product rule. And a lot of situations when integration by parts is used is when you have instances that the derivative was the result of making use of the product rule in some respects. So they just show the development of the formula here, which I'm not going to get into too much. But ultimately, this down here is the formula you want to kind of get to know for doing integration by parts. Usually, what you always want to do is kind of go through a progression of steps. I mean, try to see if a basic rule is going to handle it. If not, then try to think of any substitutions that will handle the integral you have. And only when that seems to fall apart, integration by parts should probably be chosen. So let's look at an example of doing integration by parts. So use integration by parts to find x times e to the x dx, the integral of that. So typically, what you choose for u should be something that would eventually be exhausted when you take derivatives of it, whether it be one or several, whichever the case may be. X's will eventually disappear. Now, anything I'm stating here is not going to be a steadfast rule because there's always going to be exceptions to it. But that's usually the first thing you want to try to do. Other instances, you notice we haven't dealt with integrating a natural log yet. Well, that's because the only way to do that is to make use of integration by parts to do it. And you're going to see that momentarily as well. So here we're choosing u to be x and dv to be e to the x dx. You definitely want the function that you choose for dv to be able to be integrated, because integration by parts is essentially doing some derivative work and some integration work. So here I choose x to be u, so I find out what du is, and du is just going to be 1 times dx or dx. dv we chose as e to the x dx, so v is going to be the integral of e to the x dx, which is just e to the x. Now that we have these values all set in place, now I'm going to make use of the formula we had on the previous page. That integration by parts is done by doing u times v minus the integral of v du. So when I do u times v in this instance, I'm going to have x times e to the x again, minus v, which was e to the x, du, which is dx. And what I'm hoping to get next to the integral is something I should be able to take the integral of fairly easily. There will be some cases where you may have to resort to doing another integration by parts to handle that integral. So keep that in mind. This is a process that may have to be repeated more than once. So in the end, when I take the integral of e to the x dx, I get e to the x as well. And then I put a plus c at the end because each integral I'm doing here would technically have its own arbitrary constant. But if I take several arbitrary constants and add them together, I'm just going to have yet one other arbitrary constant. So now they show you how to check by using differentiation. You know, that's always a good way of checking to make sure that you came up with the right answer. And they're kind of showing here that, you know, you end up with, if you take the derivative of what you got, you end up with x times e to the x again. To do the procedure, make sure that the differentials du and dv include the dx part of it. We usually omit the constant c when we integrate dv to get v because 1 plus c at the end is enough. The integration by parts formula does not give a final answer because you still have to do an integral at that point. And because there's an integral that has to be done, that v du, there's always going to be a possibility of having to do more to get that integral to work. And sometimes even substitution might be made. Sometimes another integration by parts has to be done, whichever the case might be. Let's see. Integration by parts should be used only if simpler formulas 1 through 7. The ones we've already kind of talked about, they're talking about the back cover, but you know, basic integrals, substitutions, things like that, if they don't work. How to choose u and dv? They go through a whole process here. But the thing is, I mean, anything that they give as a guideline here, don't think of it as a steadfast rule. These are the things that work most often, but it doesn't mean they work all the time. They're good places to start. So, because they do say it's no foolproof way, but dv should be the most complicated part of the integral that can be integrated easily. So you want to choose it to be something that looks like it's involving as much of what's in the expression as possible, but at the same time would be integrated very easily, and hopefully without necessarily having to do any excess integration or anything like that. You also want to choose u so that u prime is simpler than u. As I said, we usually say in some cases, for the most part, u should be exhaustive. So basically, if I take derivatives or repeated derivatives of the expression in u, I'm hoping that it would eventually just become dx. Again, not a steadfast rule, okay? Because there are some exceptions when we deal with that. For more specifics, these are some more general guidelines. If I have something of the form x to the n times e to the ax power, notice it's ax. It's not like a to the x squared or something like that. But if it's in this general form, then usually u should be x to the n power, dv should be e to the ax. dx is just when I'm dealing with x to the n times a natural log of x, u should be the natural log of x, and dv should be equal to the x to the n dx power. And if I have a circumstance where I have two quantities being multiplied together, as long as they're both binomial, binomial and linear, then generally the x plus a, the thing that's not being raised to the power, is what u should be, and dv should be the one that's, the one being raised to the power. But remember, there's always going to be exceptions to these rules, and generally you're not going to necessarily know for sure until you've tried it out and find out it's not getting any easier. If I keep doing any integrals, or I keep using integration by parts, and when I get to the part to do the integral again, it's not getting any easier, or I even reach a point where it's impossible to do. So we're going to go through a couple of examples here. I'm going to let you try it first. So have a good look at these things here. These are also in your textbook. So when we look at this one here, so let me ask you first. What should I let u be in this circumstance? Well, if you go according to what we had on the previous page, it works best for u to equal the natural log of x. And dv should take up everything else that's in the expression. So the x to the fourth and the dx is what goes here. So now I'm going to find du and v. The reason why in this integral here, we don't have an integral rule for natural log x. We can use integration by parts to come up with one, but up to this point we have not really had one, because generally the formula you get for doing the natural log of x, the integration of it that is going to come from integration by parts. And since there is no definitive rule for the integral of the natural log of x, and I can't let the natural log of x be dv, because I would have to integrate it, and I don't have a rule for it. I do have a rule to take a derivative of it, and that's just 1 over x dx. When I integrate x to the fourth dx, I get x to the fifth over 5. I don't put the plus c in here because just me tacking on a plus c at the end is suitable enough when I get to that point. So, with that being said, now I'm going to use the formula uv minus the integral of v du. So u times v would be x to the fifth over 5 times the natural log of x minus the integral of 1 over x times x to the fifth over 5 basically gives me a 1/5 x to the fourth dx, which I would move the 1/5 to the outside. And doing the integral of x to the fourth dx is, well, a straightforward integral. You know, it's one of the basic ones we've dealt with before. So this all remains the same. The integral of x to the fourth is 1/5 x to the fifth. I can put the plus c at the end now that all the integrals are gone. So here I'm going to have x to the fifth over 5 times the natural log of x minus 1 over 25, or I guess put the x to the fifth up here. X to the fifth over 25 plus c. So making your decision about what u is important. And what's also complicates it is what we're going to get to in the next slide. Two integrals that look a lot alike. You know, really the only difference is I have an exponent of 2 next to the x in the denominator of b, and I don't have that in a. And the reason being is, well, there's going to be times where it's best for me to, you know, do integration by parts, and there might be other instances where a simpler version is needed. So, for part A, doing the integral of the natural log of x over x dx, what should I look to do in this one? Should I be looking to do, you know, is there some integral rule that directly relates to this? Do I need to use, you know, substitution perhaps to do it, or is this one that integration by parts would need to be done? Now, since I had said that the natural log of x is often involved with integration by parts, everyone starts assuming that anytime you see it, you should try integration by parts. That's not always the case. For this one here, I can do a substitution because u equals the natural log of x, du would be 1 over x dx. And I have to keep in mind that what I have up there I have the u portion and I have the entire du portion. That's enough for me to do the substitution. So this substitution would become u du. So finish the integral and give me the solution. What would be the solution after I integrate this properly and then substitute back in to make this back in terms of x? What would be the final answer? Well, if I integrated the u, you know, there's a 1 power here, so I'm going to add 1 to that power and divide by the new power. I can put a plus c there. And then I have to go back, since it's not a definite integral, you know, I have to go back to being in terms of x. When I have a definite integral and I'm putting numbers in, I can alter the x values, which those numbers would be, into u values and just evaluate that. Or I could go back to putting it in terms of x and then put those x values in. But this is an indefinite integral, so that's not a concern of mine right now. So u was the natural log of x, so I'm going to replace u with that over 2 plus c. So that would be the final answer. For part B, it's a little different. That has an x squared at the bottom. If I look at the u definition here and du, I would have, you know, basically I have here natural log x times 1 over x times 1 over x dx. This would be the u, this would be the du in that case. I would have this part missing. So obviously, just doing substitution the way we did it in the previous one isn't going to work. That doesn't mean that substitution can't be necessarily done. So So the question I'm going to pose again to you is, what do I do in this instance here? Do I do a substitution? Is there another substitution I can come up with? Is there a rule that directly takes care of this? Or would I have to do integration by parts? Well, I do have to do integration by parts for this. Because really the only other technique we have besides substitute, there is no rule for natural log x over x squared. At least none that we've encountered yet. I mean, there are some integration rules in the back of your book, but we haven't talked about the next section yet, which deals with integrating by using tables. So, we haven't gotten to that skill yet. So at this point, it's either going to be a basic rule that you learned, which just doesn't fit either of them, any of those rules. It's going to be by substitution, but you can see when I try to do a substitution, I'm not really going to get anything that's going to be helpful to me. Or I have to do integration by parts. So I'm going to do integration by parts here. So the question becomes, I have to pick and see what u is and what dv is going to be. So tell me, in this instance here, what is u going to equal? Well, in this case here, since there is a natural log of x involved, I'm going to let u be the natural log of x. dv, I'm going to let be x to the negative 2 power dx. I'm changing to x to the negative 2 because I'm going to make use of the power rule. So now I should be able to find du and v. So du is going to be 1 over x dx. V is going to be, well, I'm going to add 1 to the exponent, so I'm going to have x to the negative 1 divided by negative 1. Right there. I was going to put a plus c there, but I don't need it. So now I'm going to do the integration by parts formula. So do the formula, and what do you get when you apply the formula for integration by parts? When you apply the formula for integration by parts, you're going to get to the point where, okay, I'm going to have basically a negative 1 over x times the natural log of x. So u times v is going to be negative natural log of x over x minus the integral of v du. So basically, I have to remember this is the same thing as negative 1 over x. So I'm going to have 1 over x times negative 1 over x, which is going to give me a negative 1 over x squared dx. And so I'm going to simplify a little bit. The negative is going to come out. It's going to become plus the integral of x to the negative 2 dx. And now I'm just going to integrate that because I'm just going to use the power rule again. So again, I'm going to have negative natural log of x over x plus x to the negative 1 over negative 1 plus c, which when I simplify, I'm going to have that as my final answer. So you can see one small change in the expression could change the whole way you would do the integral. So that's why you have to do a lot of practice. That's why Pitt has an integration bee, because integration is a skill that needs to be continuously worked on to get good at it. So in some instances, you may have multiple ways to do it. For instance, I could have taken u in this case. I could have let u be x, and I could have let, or x to the negative 1, I could have let dv be the natural log of x over x, because we integrated that already. We had a rule for that. We knew we could handle it, even by doing a substitution. So there was another method there that would have possibly worked out. So, so there may be more than one way to approach it. There might be some cases where you could do a substitution in one way, or you could do integration by parts another way, or something along those lines. So have a look at this one here. Now again, the first thing you have to kind of do is kind of go along with to see what you have in front of you, and come up with some viable options. So, which of the following options is going to be, um, you know, one that's going to successfully integrate this? Well, this is kind of a trick question because um, 3 of the 4 ways I gave you could possibly lead to the right solution. I'm going to show 2 of them. One of them is pretty similar to the other one here because when it's the first one was simplify the expression by foiling this and then carrying through, simplifying and then integrating. Simplifying the integral, um, you know, I could possibly simplify the integral, another way too, because I have x squared, I have this squared. I could think of this whole thing to make my life a little easier as x times 3x squared plus 2 squared and simplify in that manner and then eventually still FOIL it out. So there's a couple ways to simplify this. Just to be careful that you're simplifying correctly. Now I'm going to erase this because I'm just going to kind of carry out the other way of handling it. The other way is I could use integration by parts, but it's going to be kind of tricky about how I'm going to use integration by parts, because if I go with the standard way that they usually suggest that I go with it, I'm going to find that I'm going to make my life really difficult. So what I'm going to do here, method 1 here is I'm going to simplify. And, as long as I have a reasonable power here that I'm raising the binomial to, this one's squared, that's not too bad to handle. I should try to go with that. If I was trying to do one where, that was like a 9th power or a 10th power, I may not want to handle it that. Even if it's like to the 4th power, that might be a little bit too much anyway. So, but I'm squaring. So I can simplify this by saying, okay, well, I'm going to have the integral of x squared. And if I FOIL this out, I end up with 9x to the 4th plus 12x squared plus 4. And then I could go one more step and say, okay, I'm going to distribute the x squared now, which gives me 9x to the 6th plus 12x to the 4th plus 4x squared. Now here all I'm doing is basically using the addition rule for integration as well as the power rule and the constant multiple rule. So the very basic rules. So for this one here, I'm going to have, the integral of x to the 6th is going to be x to the 7th divided by 7. So since I had a 9 in front, it's going to be 9x to the 7th over 7. And that integral is going to be gone at this point. Sorry about that. Plus, that's going to be x to the 5th. I'm going to now have 12 over that. And x squared becomes an x cubed. So there's a 4 in front. I'm going to have a 3 down there. And of course, I'm going to put the plus c at the end. So that works out pretty easily. The hard part was making sure to FOIL and simplify correctly first. I could also use integration by parts. Okay. Now, you were given 2 options of integrating by parts, and if you followed the book's guidelines, so to speak, the guidelines kind of point you in the direction of saying that this here is u, or I could say the whole thing squared is u. Or no, take that back. That this should be u, this should be your dv. And if you go that route, and try to do that, you're going to find out that really quickly, you're going to end up, whenever you do your u times v minus the integral of v du, the integral of v du becomes an integral that you cannot integrate. So, so if you follow the guidelines that the book gives you, it's going to be one of those instances, it just doesn't work. So when I do this, go back to the pen here, I'm going to let u equal 3x squared plus 2 squared, and I'm going to let dv equal x cubed, or x squared, getting ahead of myself, dx. Now, what I want you to do from this point is find du, find v, and carry through the integration by parts and see where you get to get the final answer. So, does the final answer come out to be the same thing as you got on the previous page? So I had to answer a couple questions there. So let's get into this. Du would be 2 times, using the chain rule, 3x squared plus 2 to the first power times the derivative of 3x squared plus 2 would be 6x dx. V would be x cubed over 3. So now when I apply the formula u times v minus v du, I'm going to have x cubed times 3x squared plus 2 squared all over 3 minus the integral. All this over here, I'm going to make my life a little easier and just say that's 12x times 3x squared plus 2, which is 36x cubed plus 24x. Now when I multiply the x cubed over 3 there, I'm going to have 12x to the 6th plus 8x to the 4th dx. So it makes the multiplication a little easier at that point. And then, of course, I would integrate. This stays the same. I'm going to have 12x to the 7th over 7 plus 8x to the 5th over 5. I could put the plus c in at this point. And this doesn't really look like the other answer, not entirely. I mean, I do see if I distribute the negative, the only part that I have right now that seems to be mimicking what I had on the previous answer is that one. That one? No, not that one. None of them yet. Jeez, I was getting ahead of myself. I thought it came up that soon, but no, not quite that soon. So I'm at this point, I'm seeing some things that look like they would lead to the same thing, but I'm not quite there yet. So, and here's why it's probably best to use the first method, because even in this method here, I'm still going to have to, if I'm going to try to make sure it's the same answer as I had before, I'm still going to have to carry through that squaring there. So, I'm still going to have x to the 3rd. There should be equal signs following all these all the way down, but yeah, you kind of know what that. I'm still going to have the 9x to the 4th plus 12x squared plus 4 all over 3 minus 12x to the 7th over 7 minus 8x to the 5th over 5. That should be a C, and that should be a C. Sometimes I say one thing and write another. Carry through the x cubed up there. I'm going to have 9x to the 7th plus 12x to the 5th plus 4x cubed all over 3 which is going to give me essentially 3x to the 7th plus 4x to the 5th plus 4x cubed over 3. So I'm starting to see something I had in the previous one. Minus 12x to the 7th over 7 minus 8x to the 5th over 5 plus c. And I do have some like terms. These are like terms. And 3 x to the 7th minus 12 x to the 7 over 7 is 9 x to the 7 over 7. 4x to the 5th minus 8 x to the 5th over 5 is 12 x to the 5th over 5. I still have the 4x cubed over 3. No other like terms with that. And I had the plus c. And that is the same answer as I had previously. As you can see, it can be done by integration by parts. However, it was probably a little easier to do it the other way. So you're going to find that there might be multiple ways of doing it, but there's going to probably be one that clearly is easier than the other. So another thing that we talk about in this particular lesson, and I've seen some previous tests where present value of a continuous stream of income comes into play. And it's not exactly the same as the previous or the present value for an exponential function or a compound interest function that we've looked at earlier in the term. Basically, if a business or some other asset generates income continuously at a rate of blank dollar of C of t dollars per year, where t is the number of years from now, then it's called basically it's a continuous stream of income. To find the present value, you essentially, they go through all the explanation here, but you basically follow this formula here. The present value of the continuous stream of income, C of t dollars per year, where t is the number of years from now, for t years at continuous interest rate r, is given by this formula here. So essentially, you're going to do the integral from 0 to the number of years that you're looking for. You're going to put your rate of income in there, and then you're going to multiply by e to the negative rt time and dt. And it's just basically it's a lot of plugging and chugging. They don't really go into the whole explanation as to why it's a negative r, because if you're talking about a growth, and why you have something that looks like it's going to make it a decay. There's all sorts of weird things going on with this, and there's reasons behind it they really don't get into. You'll probably get into it in some other advanced business classes, or if you had to go into a more advanced type calculus course or something like that. But we're not really, it's not really one of the goals of this particular course. So just kind of know how to do the formula. So as an example, a business generates income at the rate of $2 million per year, where t is the number of years from now. Find the present value of this continuous stream for the next 5 years at the continuous interest rate of 10%. So basically, you're going to have not only income coming from, the business itself, but the income that's going to come from interest that the previous money that you've put away is also earning. So using the formula from the previous page, I'm going to go from 0 to 5, because 5 is the number of years that the time span. My C of t was 2t. I'm going to multiply by e to the negative 0.1t. Again, the r interest rate should always be converted into a decimal, dt. And now I'm going to integrate this. And most of the time that when you get one of these present value functions, you are going to be using, integration by parts to usually handle it. So we're looking for a definite integral. And since I have to use integration by parts, I kind of ignore the numbers at first, because this is one that doing a u substitution isn't going to work. So I'm not going to be able to change the numbers in root like I can with the substitution. We're going to kind of go with a route that would also work with an instance where substitution is needed. I'm going to ignore the numbers for the time being. I'm going to integrate by using whatever method it is, in this case integration by parts. I'm going to get my formula for that integral, and then I'm going to apply the 0 and the 5 at the end. So I do the integral of 2t e to the negative 0.1t dt. We choose u to be 2t. We choose dv to be e to the negative 0.1t dt. I work out my du and v values as seen down there. And then I apply the formula, uv minus the integral of v du, and they have those values up there. I can then integrate the e to the negative 0.1 t dt. And then I can simplify a bit to get this formula here. Now, I mean, we have the plus c at the end, but I would drop that because I'm gonna evaluate this now going from 0 to 5. So I plug in the 5, evaluate it. I plug in the 0, evaluate it. So I get negative 300 e to the negative 0.5 plus 200, which is about equal to 18. They probably round it off a bit. So basically, you know, what's going on here is the present value of this is about $18 million. So now it's your turn to try a similar problem. An oil well generates a continuous stream of income of $60,000 per year, where T is the number of years that the rig has been in operation. Find the present value of this stream of income over the first 20 years at a continuous interest rate of 5%. So work this out. Be aware of what everything stands for so you can make the right answer, you know, when you put it in. So again, I'm just going to use the formula. Present value, I was going to say PV, equals the integral from 0 to 20 of 60t times e to the negative 0.05 t dt. So I'm going to integrate this. Again, I'm going to have to use by parts because, you know, I don't just have e to a power. I have 60t times that. So get a little ahead of myself with the equal sign down there. I don't want the highlighter. I don't want that either. I don't want to go that far. What the heck's going on here? There we go. Oh. So I'm going to let u. Jeez. U is going to equal 60t. dV is going to equal e to the negative 0.05 t dt. du is going to be 60 dt. V is going to be a negative 1 over 0.05 times e to the negative 0.05 t, which is negative 20 e to the negative 0.05 t. So now when I use my integration by parts formula, I'm going to have the integral. I'm going to have 60t times negative 20e. So I'm going to have negative 120 t e to the negative 0.05 t minus the integral of 60 of du of v times du. So I'm going to have 60 times a negative 20 is going to give me positive 1200. Well, it's going to be a negative 1200, but I'm going to put a plus out there. E to the negative 0.05. Everything wants to work all collywumpus today. Jeez. Cooperation, please. dt. And after I do that integral, I am going to eventually evaluate this from 0 to 20. But I have to integrate what's in there first. So when I integrate that part, first I'm going to rewrite this. I mean, sometimes when you're doing integrations, and you know, there's going to be sometimes, especially with integration by parts, there's going to be portions that you have to keep writing over and over again. Please write them. A lot of times students will try to skip writing parts of it, and when they skip writing parts of it, they end up forgetting to do that part of it, and end up getting a totally wrong answer because they threw out half of the expression they got because they didn't feel like rewriting stuff. So don't get lazy in that respect, because I've seen that laziness bite some students, in the butt, so to speak, when they try to evaluate this work. But anyway, um, I'm going to have plus 1200 times negative 1 over 0.05 e to the negative. So every once in a while, randomly likes to do that. Negative 0.05 t. And this whole thing evaluated from 0 to 20. So what I have here essentially is negative. Trying to see here. I did make some mistake. That should have been 1200 and 1200 here. Negative 1200 t e to the negative 0.05 t minus 24,000 e to the negative 0.05 t evaluated from 0 to 20. Now I'm running out of space here. When you do evaluate that, and if you do it correctly, when you simplify and write it in exact form, you end up with this. Which is about equal to 6,341.79. But you have to remember that's in millions of dollars. Or thousands, sorry. I'm getting ahead of myself. Because this is in thousands of dollars. So if I have 6,341, so basically I'm going to have $6.34 million is its present value. So that's the end of that. If you have any further questions, please make sure to ask about it in class. Until I see you there, have a good day.